We'll be starting with aldehydes, ketones. First paragraph. First thing I found is that they are used in nature and in making stuff like vanillin is vanilla beans, salicylaldehyde is meadow sweet. It's also there in a face wash, I think. And cinnamaldehyde is there in cinnamon. This is covered in the NCRT video also. So yeah, they've given some very generic uses which are fine, I guess. Adhesive, paint, resin. We don't need to really remember those. I'm skipping through IUPAC except some things. Remember some structures like valeraldehyde, acrolein, thaldehyde. You can remember thal because it's in the adjacent group, that is thal. Mesitile oxide has been asked in PYQ. Diisopropyl ketone, like that. So this is the structure of acrolein. It's CH2 double bond C, single bond C double bond OH. And valeraldehyde is just with a V and an extra carbon and CH3. Valeraldehyde. From here they've given gamma alpha naming structure. So this is alpha, sorry, if it's alpha, this is beta, this is gamma, like that, gamma methyl. Then mesitile oxide, I have told you that is the aldol product of this. In the in-text question, they have asked the IUPAC structure of alpha methoxy propionaldehyde, which has been discussed before actually. It's actually very simple. If you have options on, you can draw the options out and just check if the methoxy group is in the alpha position with respect to the aldehyde functional group. So it should be like this: OCH3, then C double bond OH. So this is alpha. Sorry, basically this is alpha, right? So it's alpha position. Preparation of aldehydes and ketones. All right, we have by oxidation of alcohols. Aldehydes and ketones are generally prepared by oxidation of primary and secondary alcohols. All right, so dehydrogenation of alcohols, like uh, it's suitable for volatile alcohols. This is something that we tend to miss, is that in this method alcohol vapors are passed over heavy metal catalysts like Ag or Cu. Primary secondary alcohols give aldehydes and ketones respectively. Unit 7 class XII. I swear they have not given Ag or Cu. They've given just Cu. All right, there you can also use Ag. You can also use silver. Okay, that's the takeaway. And then we have the H2SO4 HGSO4 reaction, which is very common. Then you have preparation from acyl chloride, which you just use Rosenmund catalyst, which means palladium with barium sulfate or any catalyst poisoner. Guys, careful while using Stefan reaction. Okay, Stefan reaction, they have told an intermediate that we always tend to miss, which is R C double bond N, which is your imine. All right, it gives you corresponding imine. It's reduced to a corresponding imine. Then you attack OH. Then you attack OH, and it does this. And yep, essential to same mechanism as any other thing. Then dival H, diisobutyl aluminum hydride, AlHIBU, anything that releases like one H, AlH, LiAlH4 for example, it has four H to release, but dibyl H has only one. Okay, diisobutyl aluminum hydride, AlHIBU. It's the same thing as dibyl H. Ester are also easily reduced. Ester is easily reduced by into aldehydes with dibyl H. Okay. SOA is oxidize toluene to benzoic acids. That is the we know. And use of chromyl chloride is used for creating a aldehyde. Alright, so chromide chloride forms oxidizes methyl group to give a chromium complex. Okay, and this hydrolyzes to give benzaldehyde. So it forms the chromium complex, as you guys can see, CHOCROHCl2, CHOCROHCl2. So it forms the chromium complex, as you guys can see, CHOCROHCl2 and twice. All right. So this is the mechanism of ETAR reaction. ETAR reaction undergoes by the chromium complex formation. Anhydrous chromic oxide, or yeah, that is can be used also. So you guys can see that chromic oxide actually it reacts with this thing, acetic anhydride. So chromic oxide and acetic anhydride and your toluene group, it forms benzylidene diacetate. So I'm assuming that it forms something like this, which I actually did not know actually this reaction. I only knew directly from CrO3 you can prepare CHO, but I did not know. See, basically it forms benzylidene diacetate. Then you react that with aqueous acid. So this has to be taken care in low condition, low temperature condition, which is the what do we say? Preparation of this thing. It's in low temperature, benzylidene diacetate. Benzylidene diacetate is in low temperature. Then you have benzaldehyde. Okay, benzaldehyde. Then side chain chlorination followed by hydrolysis. So this and all everybody knows it. First toluene. Okay, first toluene forms benzal chloride. Benzal chloride is formed by toluene and CH mu. So two of these chlorine atoms have come. And then after that you have a benzaldehyde formation. Benzaldehyde is formation because of what do you say? This reaction, like we know, right? OH, then OH2 leaves, right? This is all fine. Gatterman-Koch synthesis is with COHCl, AlCl3 or CuCl, guys. Cuprous chloride. Remember, cuprous chloride is something that I forgot. Here they have told the preparation of R2CD as well. So RMGX plus CdCl2 gives R2CD plus MgXCl. So here they've given this thing Grignard reagent with a CN groups. It'll just form your respective ketone. Acylation reaction everybody knows of the free build. Then formation of cyanohydrin. What is cyanohydrin and like what exactly is it? It's just when you electrophilic, I mean nucleophilically do Cn minus nucleophilic addition, you will get cyanohydrin. And one thing that we have to note that reaction occurs very slowly with pure HCN. Pure HCN is required to make this reaction happen. It is catalyzed by base and the generated CN ion being a stronger nucleophile readily adds to carbonyl compounds yielding your corresponding cyanohydrin. They are also called useful synthetic intermediates. And yes, if they come in NCRT, if they come in mains, please put true. This part was covered in the NCRT video as well, but basically you have to remember that this is a crystalline compound. Crystalline compound. What else is crystalline? It is diazonium salt. Diazonium salt is also crystalline. Diazonium salt is also crystalline. It's a reversible reaction, and the rate of reversibility can be increased by treating with a dilute mineral acid or alkali. Alkoxy alcohol intermediate is also known as hemiacetals, which react with one more molecule of alcohol to give a gem dialkoxy compound known as acetal. So acetal is gem dialkoxy and hemiacetal is 1R1H. And this protection Mozingo reaction, everybody knows protection of ethone group, ketone group. Remember, hydrogen gas is being used. Hydrogen gas is used. Okay, I got this wrong question once where they said hydrogen liquid, but this is hydrogen gas is used. High hydrogen protonates the hydrogen oxygen of the carbonyl compounds and increases electrophilicity. Here they have given some important N substituted derivatives which we have to mug up. So first one is amine. Amine is just C double bond N. Amine is sorry, imine. Substituted amine is also called Schiff's base. Schiff's base is when you have an R group instead of a H. So imine and substituted amine everybody knows. Oxime we know because it shows GI, correct? Then you know the syn anti stuff. Then hydrazone. Hydrazone is also simple. Hydrazine is N2H4. Same way hydrazone is just you add a CS carbon in the end. Then you have phenyl hydrazone. Phenyl hydrazone is also common sense. Instead of the H on the right side, you add a phenyl group. Then 2 comma 4 diphenyl hydrazine. You know this, right? It's a 2,4-DNP. 2,4-DNP test is occurred by this compound, and they might ask the structure. So it's just a hydrazone. It's a regular hydrazone, but instead of the H2, instead of one H, you just put a this thing 2 comma 4 dinitrophenyl group. Then semicarbazone is two n's consecutively, then C, then N. It's same as Rg9. If you remember, Rg9 similar structure as Rb9. Rg9 is called a semicarbazone. Semicarbazides are this thing are without the C double bond. You're basically without adding anything on the left side. And look over here, very cheeky, they've given 2 comma 4 DNP derivatives. What is a derivative? Carbonyl derivative. 2 comma 4 DNP derivatives are yellow, orange or red solids useful for characterization of aldehydes and ketones. I think everybody knows that it's useful for characterization, but they're orange, yellow or red solids. In lab you might have only seen yellow. Wolf Kishner, we know all of these reactions. Wolf Kishner reduction, it undergoes this kind of intermediate that I forgot. But hydrazine, when it reacts with the C double bond O group, it forms a hydrazone. All right, it forms a hydrazone, hydrazone, hydrazone. And if you replace one H, it will become all like that basically. Oxidation of mild oxidizing agents can also oxidize the aldehydes. This is followed by Popoff's rule, as you guys can know that it's followed by Popoff rule. So this is the mechanism of Popoff rule. Basically, you tautomerize this and then you form this. Then after that, you just do ozonolysis, and whatever H is there, you make it OH, and whatever double bond is there, you make it double bond O. That's all. This is not necessarily to mug up. You can just logic it out. So alkaline medium, if you use silver nitrate ammoniacal silver nitrate, you'll get this. You will get a COO minus ion, and precipitation of Ag metal, which will give you the brown silver color. And make sure to know the stoichiometry. 3 moles of OH are used and 4 moles of NH3 are created. 3 moles of OH are used and 4 moles of NH3 are created in Tollens test. Filling solution A is aqueous copper sulfate, and filling solution B is alkaline sodium potassium tartrate, which is Rochelle salt. So aqueous copper sulfate and sodium potassium tartrate, which is Rochelle salt. They are mixed in 1:1 ratio before the test. Aromatic aldehydes do not respond to this test, and 5 moles of OH are used. 5 moles of OH, right? 5 moles of OH. There, 3 moles of OH are used. So 5 moles of OH are used to form Cu2O, which is a reddish brown PPT. Then you have haloform reaction. So any group that can get easily oxidized or show tautomerism can show haloform reaction. Then aldol condensation is possible in dilute NaOH and BaOH twice. Then you have Cannizzaro reaction. Cannizzaro reaction is basic, what we have learned. And carbonyl is meta-directing group. Then you have uses of aldehydes and ketones. Okay, their uses: solvent, starting material for synthesis. Formaldehyde is also known as formalin. Okay, well known as formalin solution, and used to preserve biological specimens and to prepare bakelite. Okay, which is a phenol formaldehyde resin. Urea formaldehyde glues and other polymeric products are also prepared. Acetaldehyde is used for starting material in acetic acid, ethyl acetate, vinyl acetate, polymers, and drugs. Okay. Uh, Benzaldehyde is used in perfumery and in dye industries. Acetone, ethyl methyl ketone are common industrial solvents. Butylaldehyde, vanillin, acetophenone, camphor are known for their odors and flavors. Vanillin is used for vanilla. Speaking of urea, you guys must remember this reaction. Uh, This is Wohler synthesis that we have learned in the starting of the GOC actually, I think. GOC में Wohler synthesis, and you should remember the Berzelius also, Berzelius water-heated vital force theory. All that stuff you have to remember. Please don't forget. Go through my videos and make sure it is not forgotten. So, higher number of carboxylic acids are called fatty acids. Here's an exceptional this thing IUPAC name that has been asked in PYQ. Propane 1, 2, 3 dicarboxylic acid, and it's also called tricarb allylic acid or carb allylic acid. And obviously, Ohm's gap everybody knows: oxalic, malonic, succinic, glutaric, adipic. Okay. Com- Common oxidizing agent used is alkaline KMnO4 H3O plus. Then you have Jones reagent, which forms decanoic acid from 1 decanol. Okay. Then in presence of alpha hydrogen, when you add H3O plus, then only it becomes your specific benzoic acid and all. Without H3O plus, it'll remain as C double bond O minus. So I think I had gone for a break actually. So here I was done with tricarbolic acid. I was done till here, I guess. So yeah, chromic acid. It can be prepared. Okay, this and all is done. This is also done. Oh, I was here, right? You have hydrolysis of COCl with OH minus, and then yeah, these and all are very common. Now this one is a important one. Benzoic anhydride gives benzoic acid on. Obviously, it's an anhydride, so if you put water, it will become hydrolyzed, and benzoic acid will be released. But if you have anhydride, no benzoic ethanoic anhydride, then it will give both the corresponding acids. So if it's two of them, will give both the corresponding acids. Then from esters, you have reverse esterification or trans esterification. It forms your respective product, and you can do it with NaOH as well, and then you can pass your required H3O plus. Correct. Then you should remember the styrene structure. Styrene structure has been asked in NCRT, and in JMains many questions have been asked. Then dimerization of this thing, vapor state or a protic solvent, it starts to form dimer. So aliphatic carboxylic acids are unpleasant odor. That's why in that fermentation process, no, we had fermentation in back in the alcohol phenol ether. We talked about why fermentation was anaerobic process, and that it was written that because of something, ethanol and ethanoic acid used to be mixed in the required solution, and that caused, what do you say, that cause unpleasant odor and taste. So that is the reason, because carboxylic acids have unpleasant odor. Please go through the video for alcohol phenol ether. It's written there. Remember, only in aprotic solvent or in vapor state it stays as a dimer. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. So one thing we often tend to miss is that CF3 is better than NO2 is better than CN is better than F is better than Cl is better than Br is better than I is better than pH. Okay, so from here we can notice that, bro, basically CF3COH is better than CCl3COH is better than CH3Cl2. CHCl2 COH is better than NO2COOH is better than NC is better than F is better than Cl is better than Br. It's still following that order itself. Then we have HCOH. Okay, HCOH is better than Cl, which is distant 2 from 2 distance from the carboxylic acid. Then you have benzoic acid. Okay, benzoic acid is like the HCOH is more than benzoic acid. Then benzylic acid. Then you have acetic acid. Then you have this thing, propanoic acid. Right. So from here, conclusive stuff that can be discussed is this, and this and this. These orders are, I think, very important. So first we'll write HCOH, जो NCRT, it is all in NCRT. C6H5COH, then we will write CH3COH, then CH3CH2COH. So formal, benzoic, acetic, propanoic. That's all we have to remember. These and all are just based on your normal order that they've given: CF3, NO2, CN, FCl, BRI, pH. Okay, only this HCOH and CH3COH, CH3CH2COH, that kind of stuff, it is there in NCRT. Okay. Then formation of ethanoic anhydride, they have given a reagent called P2O5. P2O5 is your what do you say? The dehydrating agent, mineral acids, right? H2SO4, P2O5. Then you have esterification that we have learned many times. I predict that this question is going to come in JMains 2026. So, esterification, mechanism of esterification, they have given in NCRT. Carboxylic acid, it'll attack by the OH group over here. Then they said that tetrahedral intermediate will form. Okay. Till now it's okay, right? Till now it's okay. But as you guys can see over here, R dash, okay, R dash OH RO plus, okay, this is coming. Then proton transfer is happening. This H is cutting and coming over here, and then this entire OH group is getting leaved, and this double bond O is donating because it's leaving. Then you just remove your H minus, and then you get your corresponding ester. Process of PCl5, PCl3 and SOCl2 is same as alkyl halides that we used to prepare, no, from alcohols. We used to prepare alkyl halides. Same side products as well. POCl3 for PCl5. PCl3 you have H3PO3, and SOCl2 you have SO2. And thionyl chloride is preferred because other two products are gaseous. And like basically they're saying that SO2 and HCl are gaseous, so they will escape out of the mixture fast. Carboxylic acid will give ammonium acetate salt. Then only after you release the H2, it will give acetamide. And here they have given the phthalimide synthesis. Ammonium phthalate is forming. Then you remove both these. Phthalimide is forming. Phthalimide is going to, you just remove the NH3 group because it's very volatile, and then boom, it forms your phthalimide. So reduction of this group, it is best done by B2H6. Best done by B2H6. B2H6 is the goat, okay, for this. B2H6 is the best. B2H6 is the best. And note that B2H6 does not happen for ester, nitro, halo, etc. Okay, it does not reduce functional groups. Then you have reductions involving you have a decarboxylation reaction, which is NaOH and CO in the ratio of 3 is to 1. It forms your RH and Na2CO3. Remember, 3 is to 1 ratio is gonna be used.